Okay, so this is what you have over here. Up. Now, what you would see that there is a new part of it which comes down in this code. So this is tutorial 3. Okay. Now you have this first part which is essentially your what is called as a data loader. The whole purpose of this part is to get your data set. Now for most of the standard data sets like MNIST, which is the digit recognition case, you already have the data sets directly available within Pytorch. So what we try to do over there is that you have something called as a data sets, and that is you import it within this Torch Vision library over here. So from Torch Vision you are importing data sets, and there's a different part of it called as transforms, which is a part of the data preparation pipeline itself. Okay. Now within data sets what you are able to do is you need to include this MNIST command over here. So the purpose is every different data set has a different data structure and a directory structure in which it is kept down over there. Now retrieving them has a bit of issues if you don't have a generic way. So how it's written down is you can go into the documentation for data sets, you will get down like for MNIST there is one way, for CFA there is another way, for Google Street View numbers, Street View house numbers there is another way, and then there are numerous such data sets which you can use. So can you just scroll a bit on the right? On the right side, I want to see that text. Click over in the bottom and scroll it. Click and scroll. So here, if you see, what it does is that it downloads this one and then goes on to stores it onto this particular directory called as MNIST. So that's within wherever your this code is kept down. So it's a // thing. So over there it creates a new directory and stores it. Now we are downloading the training data set over here. That's the reason why you will need to keep down train equal to true. Then download equal to true, what it does is that if the data set is not present, then it will download. If the data set is present already in that location, so it does not download. So the first time when you try to run this code, you will see that it takes a bit of time and it downloads the data set. Next time if you have the data set already downloaded and available in those location, then it's not going to download this one. And this is a part where you apply some sort of a transform whose job is to prepare the data according to whatever is the need of inputs to the whole neural network. Now, on this side, yeah. Now the next part is that you initiate something which is called as a train loader. Now, what this loader's job is that once you have a whole data set, so that will have, so typically over here your training data set is 60,000 images. So there are 6,000 images for 10 different classes, which makes it 60,000 images. Now if you try to push all 60,000 images in one single shot, then it will not go through the network. You will have to take a few at a time. So the lowest which you can take is one image at a time. The maximum you can take is 60,000 if somehow it's permitting for that many to do a forward pass through your network. Now for each of them, when you take them, then it needs to define like from where is it loading this one. So here it sets that I need the data loader working on the training set, which we have defined in the first line above it. Then we go to this point, which is how many images will I load in one shot, which is called as a batch size. Now this batch size is something which is defined over here, and then we have kept it down to 256 images in one shot, which will go down. So you have 256 images which go through the network, you calculate all the derivatives and everything, you update the network, and then you take another 256 images and you pass it. Now this 256 as a number has a significance, but a bit later on we will come down to why do we have 256. Sometimes you would see that it would be 128, 64, 32, 16, 8, these kind of, it will always be in a power of 2. And there are reasons why that's made in that way. Shuffle is a condition in which what you do is that you are going to run a multiple number of epochs, which is a multiple number of iterations. Over every iteration, is the order of images in every batch going to remain the same, which means that if I have a data set, now I can chunk it out like 256, 256, 256 like this and keep on going. Now the question is, next epoch when I pass it, do I have the same 256 going in the first one or not? So generally we don't want to have that, we would like to have a different combination inside over there as well, and then that comes down from a factor of what is called as a stochastic randomization in order to ensure that there are no local minima conditions. Now that's an extensive proof which we are going to do, exactly like how that helps you come out of these local glitches. Now for the time being, you can just remember over here that this setting this shuffling over here is something which is needed for enabling that stochasticity to come into it. And then there is this interesting part which is called as num workers. Okay. Now most of our systems essentially have a parallel compute environment for us. Okay. Now your computers will have a CPU. A CPU will have multiple cores inside it. Each core will have multiple processing units inside it over there. Okay. So you can essentially start some sort of a parallel processing pipeline over here. Now all of your data resides on a hard drive over there, which is much slow in access as compared to RAM or the speed of your CPU. Now if you want to really have this 256 elements pushed into as a streamlined mechanism, then what you will have to do is, it takes a substantial amount of time, almost 4 times more time to read it from the hard drive than to copy something from RAM and give it to the CPU over there. Now for that purpose, what we do is we have 4 parallel channels of reading the data from the hard drive. So they are all slow channels, but typically if I am able to initiate 4 parallel workers over there, then while the first 256 images is being pushed into it, the next 256 into 3 are being read, and whichever becomes immediately available, this goes through it. So it's a standard pipelining procedure which is followed over here. What you need to define is basically what's your pipeline length over here. So that's a concept which you get from your parallel programming and operating system concepts. So just remember that you need to define your pipeline length, and we in general for most of your Intel based PCs it will be 4, other than Xeon processors. Xeons will can make this as 6, or if you have multi-core process like dual processors on a system, you can make that even 12 over there. But for our PC based system, this is going to be 4, and that is limited essentially based on how many RAM access channels do you have through your RAM bus controller to your CPU. So for your general PC case, this is going to be limited at 4. Okay. Similarly, you have the testing set over here, and you write down the same thing over here. Now the point of discriminating a testing set is that your train is set as false in this line. So when train is set as false, that is what downloads the testing data set over there. Now the point is you can apply transforms, and what the only transform which we do over here is that you convert an image which is essentially a NumPy format or a Python imaging library format to a tensor which is in Pytorch. So you just need that image to be converted to a Pytorch tensor, and that's the transform which you are going to apply. So now if you print the size of these data sets, you would see that there are 60,000 samples in your training set and 10,000 samples in your testing set. Okay. Now this part is straightforward. This was the model definition which we had created, 784 neurons, 200 neurons, to 10 neurons, and then the forward pass over there. Now in line 7, here you would see that what you are trying to do is, you are trying to find out whether your system has a parallel programming environment available or not. And for us, the acceleration on parallel programming is essentially through CUDA. So this part just finds out whether there is CUDA available or not, and in case there is CUDA available, then you need to have the model transported onto your GPU environment. Now GPU environment porting is generally a function call, and generally a typecasting function call. So if you do any variable dot CUDA, then what it does is that the compute is shifted onto your GPU. The variables associated with computing on the GPU is shifted onto from your CPU RAM onto a RAM of the GPU. So in fact, your GPU will have its own local RAM itself. You will have to copy all of these. Now it makes it easier for us on a high level construct that you just do a typecasting operator as .CUDA. Now once you do that, we try to print it out as well. So if GPU is available, then you see that there is a GPU available to do it. Now trying to have a construct like this, say use underscore GPU, you would see that throughout these programs which we write, we typically have this use underscore GPU. Now for heterocompute environments where you might be running on Xeon processors or FPGAs as well, you can actually set a multiple number of these flags, and using these flags you can automate the whole process. So it does not need to essentially, explicitly you don't need to code one set of program for GPU, one set of program only for Intel Xeon class 4 processors, one for Core i5 processors, but then you can have this single environment set down where the code, based on asserting whether that particular function is available, it's going to invoke that service in order to run it. Okay, so let's go up. Now comes the part of training. Now here what we do is we use binary cross entropy, which in Torch is defined as a cross entropy loss. That's the function. Now that eta factor, which is your learning rate, over here is set as 0.1. So you can vary. So you can make that 1, you can make that 10 power minus 2, 10 power minus 3. And in fact, I would suggest that you keep on varying that and check it out. Okay. We are going to train over 50 epochs over here and initialize these two losses, a loss and an accuracy on the training part of it. And then we start this whole part. Now look into one part. There is these two factors called as running loss and there is a running correlation factor. Okay. Now the whole part, running number of corrects, which is to get down your accuracy. The reason for this is that you will not be able to push all the 60,000 images together. You have a batch, you are putting down 256 images one at a time. So whatever loss you are calculating and how many number of correct predictions are there, you are going to have it only out of this 256. But then you will have to accumulate all of this over all of such small batches which will come. So there will be 60,000 divided by 256 and the ceiling on top of it. This is the total number of runs which you will do, or that's the total number of mini batches which it has to look into it, and you will be aggregating it over that. So these two running variables are essentially to do that. Okay. So let's get into this. The first part is you load the data, and that is what comes down from your data loader. Now that you have that, you essentially need to know if there is a GPU. That means that your model has already been sent on to the GPU. So the data now has to be sent on to the GPU, and this is this part. So you have a inputs.cuda, and then this inputs.cuda as well as labels.cuda, the whole job is that you typecast it. By way of this, you are sending something from your CPU RAM onto your GPU RAM, and that's available on the GPU. Next, what you do is you zero down all the gradients. So this gradient part is something interesting. All of these Nabla network as well as Nabla loss, whatever you had, these are aggregated over all samples. So essentially it's a scratch pad where the previous value is stored. But then if I have a batch which has been passed, you updated the whole process based on that. You don't need that previous batch's gradient anyways to be stored. You need that removed out. So this thing has to be initialized so that any previous gradients are not stored before you start the whole process. Now you start this. The first part is to predict out the output. That was the forward pass of the network. So you give the network and the inputs which goes over there. And here you would see that you have basically put this inputs.view, and the whole purpose of this view was to linearize it into a 1D array. That's what we had discussed in the previous class. Now from there you get into your predictions, and the prediction over here is essentially to do a argmax over all the soft predictions which come down. Now the moment you do this argmax and you get down your predictions, you will have a 0 1 0 1 kind of a thing. So one particular class will be 1 and everything else is going to be 0. Now that you have that, you find out your loss, and the loss is calculated through criteria, and criteria is that loss function which we had defined above as cross entropy loss over there. Now once you find that out, you can accumulate the loss, which is through this running loss, as well as you can find out how many number of corrects are there through this part of it, how many correct classifications you have done. Now that you have done it over all of these, so you can find out what is your total loss over here. Okay. Now your total loss is something which you are going to use in order to calculate your gradient over that loss. So one is you will have your nabla of the loss function over there. So this total loss dot backward is a nabla of the loss function. Okay. The next part is that you need to update all the parameters inside your network. So first is get down all the parameters. So this is what comes down over here, this part in for f in net.params, where f is going to be each of these parameters which are present within your network. And in the earlier class when we were building up the model, you did see that net.parameters is what is pushing out all the parameters. It gives you all the different parameters which are present over there in terms of its structure. So you look through this structure. Now what you are going to do is that you are essentially going to subtract from the parameter this part of it. So there was this wk plus 1 is equal to wk minus eta times your del w of jw. So your del w of jw is this part, f dot grad dot data. Eta is learning rate over here, and the whole function of wk minus this whole part is what is within your f dot data dot sum. Okay. Now this is a standard way in which internally it's implemented over there. The way of using this construct is because you have different size tensors for each of them, and some of them are scalars. You will be differentially implementing them and impacting every single layer over there. Okay. Let's go up. Now next, once that is done, you can find out what is your total loss over all the batches which have run within an epoch. that is to calculate your epoch loss and your epoch accuracy. Now once this is done, your training is keeping on going. Now within every single epoch, I can also find out what is my, so these are training losses and training accuracies which essentially are saved over the whole process. So there are 50 epochs on which I am calculating, so I'm keeping on storing that one. Now once that is done, we can get down your training and like we can basically start this process and keep on printing them. So this part is optional, you may print, you may not print. Now if you keep on going across these epochs, you would see that the training accuracy is gradually increasing over there. The loss is decreasing, the loss is a binary cross entropy, so it's a different kind of a loss, but looking at accuracy makes it much more easier. Now here we have been able to come down something to 53% accuracy for a 10 class classification problem, which is not that bad. I mean, in the worst case you would have got a 0.1 accuracy, which is a random guess, but we are much above that, so it's a good case, but it's still growing, it's not yet convergent. So can we go a bit low? Now what we do is we basically plot all of these. So you had it stored in terms of your array, so let's plot and see them. So this was how the loss is decreasing, and just scroll on the right. And then here you would see how this accuracy is increasing. Now you see one point where you have a nick coming over here. It just glitches. Now these are typically those conditions where your learning rate was possibly high, so it basically skipped off from one and went to the other point. In that point, like momentarily wherever it landed, it got a very high accuracy, but then again it went on to some point. Now my assumption is that this was a local minima where it started, so it skipped over here. Now it is going somewhat towards the global minima position, but then you will have to really experiment with that learning rate over there. Now eventually when we progress more through the class, we will come down to points of how to auto-tune learning rates, whether learning rates are constant over a period of time or they keep on changing the more you keep on doing your training process as well. Now once that is done, we go into evaluating this whole model over here. The whole purpose is that you have a test data, which is what the network has not seen when it was getting trained, and my objective is that on that test data I would try to see how is it performing. So we say that on the training side it has a 53% accuracy, but on the test side it has a 55% accuracy itself. So that's about, I think that's it. Yeah, that's about this one model. So similarly you have tutorial 4. If you go back onto the main repository, you will get down that. Tutorial 4 is the same kind of a process done over LeNet. So